the energy and the momentum, something like this, square root of Q squared plus, let's say, equal masses, then it's easier. Then we just have 2 here. So if you have 2 equal masses, then that's the relation. Is that correct?
Probably not.
Something wrong here?
Well, you first, because we are talking about different channels, so you should put an index, an MI.
Exactly.
EI equals M.
That's you could look at it.
Next step.
Okay, so that is the relation, I think. Now, if you have an amplitude, the amplitude is a function of the momentum. So, if you want to study the poles in this amplitude, then you go to the so-called complex chaos plane. So you have here the imaginary part of K, and here the real part of K. And then you find somewhere a pole, say here. Now, this pole normally has a counterpart. Let's try another color. Normally poles are in pairs. So you find these 2 poles. Now what happens if you...
Can you explain this obvious, but why they count in pairs?
Yeah, there was a reason for that. Let me see the
Sparse reflection principle.
You have S cross equals 1. Now in the case of one channel, this is just star. So that means that S is written in the following form. It's probably E plus pole star divided by E minus pole. I think that this gives exactly the correct relation. If you do S times S star, what do you get? E plus E star times E plus P divided by, oh, maybe there was also a minus here. And there are 2 minuses here. Divided by E minus P star times E minus P times E minus P star. And that is correct, that's one. So, I have a pole in S in P.
And the 0 in P star.
And the 0 in P star. But the pole is in E. Now if I have to see, well, let me see how it continues, this story. Because I want, the pole is in the energy. But now I want to study the pole in K squared. So I get here something of the type K squared plus M squared equal to E squared over 4. Or something. So the poles in K are related to that by a square equal to, so the pole in K, let's put it this way, the pole in K is P squared over 4 minus M squared. That's correct? Yes. And so there are, this is a squared relation, so there are 2 solutions, and the 2 solutions is this one and the other one.
Okay.
No, but I don't understand that. This doesn't follow from that relation.
No.
Because if it's they should be mirror image. It's a square. Why should they?
This is not K squared. This is just, wait a second, this is a positive real and this is negative real.
Yeah.
Nothing more, the imaginary part is the same.
Yeah, so where does the square of this go? The square of this goes here,
Yeah, that's the first real sheet.
and the square of this goes here.
Yeah, that's the second real sheet.
And how do you compare with that?
No idea. Absolutely no idea.
Then there is something that doesn't.
I cannot, let me say, I just talk with my experience. I don't
Okay,
know
then
how I
you
can
maybe
describe this.
tell us tomorrow, okay?
Or maybe not. But I will certainly find it. I'm sure that these poles are there
Okay.
because they are very important. If you vary the overall coupling constant, these poles move. And this pole moves here, or that depends on the angular momentum, or here. And that pole does exactly the opposite, so they meet here, both of them. And that's one meet there. And then from this moment on, things go differently. One of them goes here, and the other one goes here.
Right.
So you get a pole which goes very deep, and you get a pole which turns into a bound state.
Yeah,
That's
you understand that? You have a resonance, has a positive real part, or a negative imaginary part. That's the important point. A negative imaginary part. That's the resonance. Now, if the real part becomes zero, the imaginary part, if it's negative, then you have a virtual bound state. If you have the sort of state where the k, real part of k is zero, the imaginary part is negative, that corresponds to a virtual bound state. And if then the imaginary part becomes positive, it becomes a real bound state.
Okay, you write the different situation on the table, so then we can discuss, because it's not, for you it's obvious, for them it's not obvious.
No, for me it's
Because,
not obvious. I'm just talking about my
I know, but
experience.
you know, a resonance is a
So-
pole in the scattering matrix
This is,
that has a width, so it should be with the,
at this point,
so in the width.
No, a resonance is a pole in the S matrix with an energy that has a positive a real part and a negative imaginary part.
Exactly.
Yes. In the momentum plane, the real part can be negative or positive, but the imaginary part must be negative.
Ecco, so there are two different representations. One in the momentum plane, and the other. This is the first one.
Yeah.
You can plot this both in the momentum space plane or in the energy plane.
Yes.
Mm-hmm.
So in the momentum plane, repeat. So then it remains.
In the momentum plane, you have doubling of poles. So you have one a pole in energy is doubled in the momentum plane.
Exactly.
And then when a resonance usually becomes first a virtual bound state. In energy it means the energy goes from positive to negative.
In energy.
But if the energy becomes negative, so below threshold, it can correspond to two situations, either a bound state or a virtual bound state.
Okay.
The bound state, the relative momentum has a positive energy, positive imaginary part, and the virtual bound state, for a virtual bound state, the momentum has a negative imaginary part.
Okay, so explain a little bit better what does it mean with a simple word or a virtual state.
It means a virtual state cannot be a stable state. It cannot be represented by a wave function. Because
the state is written something like I don't have pencils which are on.
So let's say the double pole that you see in the momentum plane, in the energy plane, obviously you see only one.
If the K is, so now you have several situations.
Yeah,
If
distinguish
K
the
is real, then this is oscillating.
Exactly.
And an oscillating thing describes scattering.
Exactly.
If K is purely imaginary, say I times kappa, so purely imaginary, then you get damping.
If kappa is positive.
To the minus kappa R.
So this
So
is
that
a
gives you a
bound
bound
state.
state.
It's a bound state.
But if you have a K which is, let me say, a real part plus an I K imaginary part, then you get something strange. So you get E I K real R minus K imaginary R.
Okay.
Then you get something which is on one hand oscillating and on the other hand damped.
Yeah, but if
So
it's damped, it's not, yeah, but usually, for a resonance, the imaginary part is negative, so you get something that blows up. Okay? And if you have virtual bound state, the real part is zero. Then you have a purely real.
So for the virtual, the real part is zero.
Yes.
Equal to zero. So there is only the oscillating part.
No, it's the opposite. Not oscillating. It's
No.
either damped or it's exploding. If it's damped, it's a bound state. If it's exploding, it's a virtual state.
Okay, if it is exploding, so a virtual state is a state with the, let's say, the real part negative.
Zero.
That means that it's exploding.
Imaginary
No, the
part.
imaginary part is negative.
Imaginary.
Yeah, sure.
But imaginary part is, see, the imaginary part, okay.
Yeah, but I mean the virtual state, but they should understand the virtual state is not a physical state. It just means that your S matrix has a singularity in a different Riemann sheet. But if the singularity lies, so if it's a question of analytic continuation. It is an S matrix is an analytic function with the exception of an isolated set of simple poles. And this analytic function can have poles in different sheets. Different sheets.
Then now we have to talk about the sheets. That's the point.
Now, a virtual state corresponds to a pole that is not on the physical sheet, but it's not far away. So that means that you see the influence of the pole in this analytic function. If you get close to it, by going to the energy goes to zero, the analytic function sees the nearness of this pole. So the amplitude goes up, and there is a classic example of that, which is the nuclear-nuclear phase shift. Yeah?
Yeah, you are interrupting me all the time.
Yes.
No, but this has to be.
We first have to talk about the sheets. They still don't
You're
know the
saying,
sheets.
for example, in the case of the deuteron, the deuteron is bound.
The deuteron is bound.
But then there is the other channel.
There's not another channel.
No, exactly, but with another spin, let's say, angular momentum, in which you have a virtual state.
It just means that the analytic function has a singularity close to the physical region.
Okay, so in that case, I think you should define the physical Riemann sheet and the other one which are not physical.
Right.
Because we don't know.
Yeah? Okay, let's see. So what are the sheets? If I remember well, I think this from here to here is called the first sheet.
Yes.
One. And this continuation from here to here is called second sheet. And why is that? Because if you calculate the square of the first sheet, then it just goes like this.
In energy, go all the way around.
So you have one sheet.
Okay.
In energy.
In
There's
any
only
case,
one
it's
sheet.
a one. Okay.
And then the second one is just another time round.
Okay, good.
We have another time, the whole energy plane.
1, okay. I can do second. Okay.
Is that correct? Did I say it correct?
I think so. Because it's the square root is a.
This is important. Eh?
It is a
You say
double
this,
valued.
you say this wrong, then we are completely wrong.
Maybe you can say it the other way around. Start from the energy and go to
Probably
the
it's better because you are more sure that you know.
because you take the square root, which gives you have to define a cut in the plane.
Exactly. Go in the other direction.
In the other way, you start from the energy.
Yeah, but the cut we have defined normally here.
Yes.
So you pass from one sheet to the other, passing through this cut. But I'm suddenly a bit confused
Exactly.
about the imaginary part of the pole position. Why should that be negative in E?
For the resonance,
Yeah.
because it's the unphysical sheet.
But also the physical sheet has a negative imaginary part of the sheet.
No, but moreover, you should define the physical sheet.
That's what we are trying to do now. But I thought the definition was this. But if I square this, that point comes here. Or not.
Yes, it does. But you should go the other way around. You start from energy and you go to the K.
Exactly.
No, but the sheets are defined in momentum.
Yeah, that's right. That's why you should take the square root. For each threshold you have a K, which means that for each threshold you double.
One threshold.
What? Yeah, okay, so if you have one threshold, it means you have only two sheets.
Yes.
For each time you take a square root, you have a
Pass to the sheet through this thing. So you have to think about it as two layers of function values. On this point. But I'm trying to see if I do everything correct. It doesn't correspond exactly to what I wanted. So in this case, what do I have? I have here, I have, let's say, a kappa, which is a real thing, times I, E, I,
no, but don't write the kappa in
some things. Yeah? Now, if I square that and add M, what happens here? So I get the energy squared over 4 minus M squared equals K squared. Is that correct? Yes. Now K squared is kappa squared EI 2I phi. And now I want to go back to what happens in the energy plane to each value. So I get that energy squared is 4 times
Well, you started from that, so you go to
kappa squared E2I phi plus M squared. Yeah. So for kappa is 0 radius here, 0. I certainly get E squared is 4M squared.
yeah, it's 2M, that's the threshold.
So here should be 2M and not M. That's already 1 error. Then, if I go around 4M squared, so now we are correct with 4 at least. So this is 4m squared plus 4 upper squared. Now if I go around the 4m squared from 0 to 2 pi, because here is phi equals 0 and here is phi equals pi, then I go 1 time round here. So this 1 time round is correct. And then I pass to the other sheet, and here I have the other sheet, which is on this side.
So when I do the second part,
so here I still have phi equals pi,
okay,
and here I have phi equals 2 pi.
okay. From the when I am on the second
On
part,
the second Riemann sheet,
I'm doing the second circle. I am on the other sheet. Let's say on the other sheet.
exactly.
So.
So there are always 2 sheets. Now if I have inelasticity, let's for instance take a pion and k-on. So then I have 2 masses. And that means I have to define 2 different momenta, linear momenta. And if I do 2 different linear momenta, so then I can say it's either K1 and 1 or it's K2 squared. In that case, I get 4 Riemann sheets. Because in energy, if I just continue this, in energy somewhere else, then this was M1, and here we have a second one, where the energy is equal to 2 and 2. Right.
Sorry, you should define what do you mean when you have inelasticity.
You have more than one channel.
So if you have more than one channel, okay.
You have more than one channel, but that means that now you have 2 K-planes. There's only one energy plane.
Yes.
So we have more than one K-channel, K-plane,
Yes.
but only one energy plane.
Yes, the energy is the same for everybody. So we get then here real part of K1, imaginary part of K1, and here we get imaginary part of K2 and real part of K2. And then we suddenly have 4 sheets.
Okay.
Because we can have this upper part combined with this upper part,
Okay.
that's sheet 1. This lower part combined with this upper part, sheet 2. Then this upper part combined with this lower part, sheet 3. And finally, the 2 lower parts, sheet 4. So you get 4 Riemann sheets.
Just one example from a physical situation where they really talk about the second sheet. And that is indeed for instance, the F0980.
For?
The F0980 resonance, which couples to pi pi and couples to kk.
Okay.
And when they talk about the second sheet pole, because you have a pole on the second sheet, but also a pole on the third sheet, which is not far away. Usually the pole that is tabled in the PDG tables, that's the second sheet pole. And what does it mean, the second sheet pole? It means that for the lowest threshold, the pi pi, it's open, which means that the K1 has a negative imaginary part. But with respect to the second threshold, kk, it's closed, which means that the imaginary part of K2 is positive. And that's conventionally called the second sheet. I mean, here it looks symmetric. I mean, you could call this one the second sheet because the upper one of the first of the one and the lower one of the other, or the other way around. But the convention is if you have two thresholds and the resonance is close to the higher one, then the second sheet is called by definition that one where the lower threshold is open and the upper threshold is closed.
Okay, and then
that's convention.
By convention, and the pole plotted by the PDG correspond to that.
Yes.
Okay.
But this pole may, although by convention it is the second threshold is considered closed, the pole may nevertheless end up above that one, the real part. Okay. It depends, because it's very close. We know that the pole of the F098 is very close to the KK bar threshold. And it is a little bit model dependent, maybe analogy dependent, where it will come out, a little bit above, a little bit below. But the convention is what you call the second sheet pole, is that one where the relative momentum for the KK channel has a positive imaginary part. That's the convention. Because sometimes people, the experimentalists, they use simple designation, they don't explain in detail, they say second sheet pole. And you have to know what it means.
So analyticity of the scattering amplitude is actually measured in momentum and not in the energy. So for the energy you have cuts.
Nee, it's all the way around. In K you have cuts.
Okay,
In energy you don't have.
K goes, there's no cuts at
But
all.
K is the square root of the energy. And the square root is a double valued. The square root causes the cut. Just like the log function causes the cut.
Yeah, but the cuts are in my energy plane. There I find cuts. In the momenta things go completely smooth. There is no, what kind of difficulty do I have to go from one sheet to the other in momenta? Zero. What kind of difficulty do I have in E? Then I have to know, oh, what square root do I take? This one or that one? Because there are two square roots.
Exactly, which one and what
And
has to
so
take?
the analytic continuation in E is a difficulty. If you define your scattering amplitude in K1,
Okay.
K2, K3, K4, K5,
Right.
you can vary them at will, no problem.
So,
But
so
in energy,
Yeah.
you have every time to look for all Ks, because if you have 10 channels, then in each of those 10 channels,
Yes.
you have this
Right.
choice
Yes, absolutely.
in each of them.
so which one do you define the physical shift? Physical
Physical sheet.
It's both positive.
That depends. The physical sheet above all thresholds is this one.
The first one, the plus plus.
The plus plus, that's the physical sheet.
Yeah.
And all the others are actually invisible.
And so, it's a stupid question. So, why are you calling that physical, the other physical?
Oh, because it's you want to see the energy.
Okay.
Because what you can measure only is real.
Right?
You cannot
Exactly.
measure anything else.
Exactly, I can only measure that. That's it.
Exactly.
Real, and
Yeah,
that means
This
more
for me
And
is
the cut lies, in
Momentum-
fact, lies just slightly below.
positive.
The cut is epsilon below the real axis.
the real axis.
Yeah, that's with your epsilon method. But if you don't do epsilon method, you just go to K. K-on is also positive. So the momentum is also positive.
Okay.
So you have both positive. And that's the physical situation. So the physical situation is when you are here positive values.
Yes.
Okay.
And now you connect to that this sheet, phase 0 to pi.
Okay. So, another stupid question. So, why the particle data group in the end, there is a convention that they plot, they give the pole as the poles that correspond to a non-physical sheet. You said
Because
that.
by definition a resonance lies in an unphysical sheet.
Because by definition, exactly.
Yes, a resonance lies in the unphysical sheet.
You want something of
Yes, because you can see in the other,
lifetime
plot.
T over tau, that's what you want.
Essentially
Something
that.
which dies out
Exactly.
according to a lifetime.
Exactly. So
that
then it
means,
is in the physical sheet.
That means that the energy should be the energy, because you can substitute this just by the energy.
Exactly.
And you get minus E T.
Okay.
Or let's say, now let's write it this way, E T.
Okay.
And that should be part of the expression, general expression of RT.
Exactly.
Now, so what do you have to substitute here? You have to substitute E equals I.
A negative.
Negative?
No, imaginary.
Just imaginary. Now I get positive imaginary part, that's wrong.
Yeah,
So
but
let's
that's
make
not.
a mistake somewhere.
Where is it?
Do I make a mistake here?
Yeah, but this is, no, but you are. Resonance is not. You're confusing resonance with a bound state. A bound state is something that has.
Dies out in space. Resonance is something that dies out in time.
A resonance is something that's done in time.
Yes, exactly.
Yeah.
And now I'm just confused about why this should be positive.
So this is time in time. It's correct in time.
Maybe this is a minus here.
Probably.
That's probably the reason which that we have to check whether that's right.
Okay.
But if it's a minus, then it's correct, and you need here minus E, and that means that you need.
That has probably to do with
One moment.
Then you need a negative imaginary part.
Then you need a negative imaginary part
resonance,
for the resonance.
Yeah.
Okay. And
probably
so,
that's the convention of.
sorry, if you need a negative imaginary part, convince me that it lies in the second sheet. Doesn't it? From the picture
because you also have this oscillation, eh? I think you just have something like
also in the first sheet
IKX, which is let's write a P here, not to understand too much. X, so which is something like E to the IKR minus IET or something like that. Yeah. So you need something which damps out
in
time after resonance.
I wanted to convince me that it belongs to the second Riemann sheet, not to the first.
Yes, that's what I
So
tried to find.
if you simply say, okay, it should have a negative imaginary part, but could be also in the first sheet. So this is not the explanation.
Yeah, but you don't want it to be a bound state.
No.
In a bound state you get if you have a positive imaginary part in space.
In space. Okay.
You put here the positive
I
imaginary part
understand. In space.
in space. Yeah? So positive imaginary part in space, that means it's somewhere here.
Okay.
This
Somewhere
is the
here,
first.
positive imaginary part in
Yeah,
space.
but that's not what you want.
So this corresponds in the energy plane to the first sheet.
To the first sheet, yeah.
Okay, so the bound states in the energy plane correspond to
To
the
the
bound
first
state.
sheet, yeah, that's a bound state.
While on the contrary,
And it has no imaginary part in the energy because the bound state is on the real axis here. Must be on the real axis, so there is no oscillation,
I am,
so to speak.
this is correct,
Yeah.
okay?
And then, if you want the resonance, if you have a negative imaginary part
Yes.
here, then you get here something which at large distances blows up, but this damps out in time, so there's no big
Exactly,
problem.
okay? And so you are in the second sheet.
I think the matter is
Okay.
causality.
You have explained
More or
well.
less.
Causality, I think it's causality which forbids singularities in the upper half plane energies.
Yeah, but I'm trying to
No,
give a simple
yes,
argument.
even
Causality, I think causality forbids singularities, poles in the upper half energy plane.
in the
Upper half.
upper half.
You cannot have poles in the upper half. I think it's because of causality.
I think there are poles there, but
It has to do also with the retarding advanced solution. We're using retarded solutions, and that is because of causality.
Causality.
Yes, yes, yes.
Okay, but in any case, it's given qualitative explanation.
Yeah, go to standard
So,
text.
so
at least we can
now-
understand
now-
that bound states correspond in the energy plane to a pole in the first sheet. While on the contrary, resonance to a pole in the second dimension.
And also the virtual state is also the second sheet.
Also the virtual state.
Yes.
But then, sorry, but since for us, at least the virtual state is not so common. No,
But in nuclear physics is very, very well.
I know, but I know that, for example, in, let's say, in atom physics, in molecular, it's more difficult to understand.
But Eef will show some virtual states, very nice. How a resonance, if he can show pole trajectories of resonances as a function of the coupling, which first become a virtual state and then it becomes a bound state.
I understand, but this is very nice. But I wanted the definition before that you
For virtual
showed
state.
the nice picture. The definition.
The definition of virtual state?
Uh-huh.
It's a singularity in S matrix for negative energy.
Aspetta, singularity in S matrix.
Yeah.
For
Negative energy
negative.
on the real axis.
Momento, negative energy.
So the negative real energy.
On real axis.
Yeah, on the second sheet, the unphysical sheet.
On the second.
Or unphysical sheet.
On physical sheet. So, which is the difference in respect to a resonance?
It is different from resonance indeed, because
also a resonance is a...
Because a resonance can be observed in the scattering process, the decay product, while a virtual state you cannot observe directly in an experiment. You can see it indirectly. Indirectly, and I would like to give one example.
Okay, but on the plane, on the
don't
energy
spoil my
plane.
picture.
I don't boil, I just show in a small form.
On the energy plane, please.
Just now, let me
Put
just give
across-
this example from physics, okay, from nuclear physics.
Okay.
Nuclear scattering,
Yes.
or no neutron proton if you wish. You have the triplet S1
Exactly.
coupled to triplet D1, and you have the singlet S0.
Okay.
This is parallel spins, this is
Yes,
anti-parallel
yes.
spins. Now, first in the triplet, the phase shift goes like this. Yeah. Okay, this is the triplet S1, triplet D1. Yeah. So it goes to pi. Okay? Which means from Levinson's theorem, yeah, it's a bit, this is about 300 MeV here, so it's not very nicely plotted, but never mind.
This is the triplet
Triplet S1, triplet D, the triplet S1 phase shift. Okay, this is the triplet S1. The triplet D1 looks different, but they are coupled.
Okay.
So it goes to pi in the origin, and from Levinson's theorem, you know, because then at infinity it goes back to zero, you go that there is one bound state.
Okay.
And that's the neutron. Okay?
This is the neutron simply.
What happens in singlet S0? It's relatively similar here. It goes like this. And this is at very low energies. I mean, this is of the order of 10 here, MeV.
Okay.
And this goes to about 65 degrees.
Okay.
And then it goes to zero.
Okay.
And from Levinson's theorem, you know, since there is no difference between the phase shift at zero and infinity, there is no bound state. It goes to zero effect. But why does it go up so much here? Because it feels the pole here on the wrong sheet.
On the second sheet.
Yes.
The second sheet.
It feels the pole. It's just analytic function.
I understand.
You get very close to that pole.
I
Okay? And you can also see it in the scattering length.
Ah, it has a...
In the singlet S0, the scattering length is about minus 23.7.
Yes.
Yeah? What is the unit? Is Fermi, huh? Scattering length. And in the triplet,
They are similar.
it is plus 5.2, I think, if I'm not mistaken. This is a huge number, which means that the energy of the virtual state is very small. I think it's of the order of minus 0.5 MeV. While the energy of the deuteron is minus 2.2 MeV. So the pole of the virtual state is much closer to threshold than the deuteron pole. But it's on the wrong sheet. The deuteron pole is on the right sheet, on the physical sheet. Mm-hmm. And this is on the wrong sheet. Okay. And that's why the phase shift, although it starts feeling it, but it has to go back to zero.
Okay.
Yeah. Now I just want to give an example of how poles move if you move with the coupling. So say that you start from, and let's start here, that you start from an harmonic oscillator state. Yeah, let's say you have calculated for your harmonic oscillator that this is your ground state, for instance. Mm-hmm. And now I start coupling in the Meson loops. Then this pole starts shifting. Down, 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 down. But then it has a very specific way of going here.
To the threshold.
And that depends now. There are some, or let's say most cases, which go this way and then continue. So it is increasing coupling this direction. But there are a few cases, and those are interesting, where it goes this way. And then...
No.
Oh, no, in this plane not. So
no, in energy it's not like that.
Yeah. I know. I was already mistaken. Okay. Then it passes here, comes here on the real axis, has to go back to this place, and now this is the piece that what George was talking about. Here it is a virtual bound state. And on this side, it's a real. It has no imaginary part, I just draw them on different sides to have distinct.
Yeah, in energy it's just real and negative.
And what is their difference? The difference here is that in the K-plane, those go, sorry.
Yeah, that's okay.
Those go, no, it's not okay. It's more like this. And then they go to the real axis. And they go smooth there.
Yeah.
And the others go this way and then up.
Or down. There are both two of them.
Yeah, okay. You draw the second one,
Yeah.
I didn't do that. And that's also here the case. So you have a virtual pole which from here goes down.
Yes.
But this is different. And what is the difference? This one is exclusively S-wave, and the other one,
Or higher waves.
this one is the higher wave, so P, D, etc.
Can you repeat this? So why the one is only S-wave?
If it is in an S-wave, so if we are talking about S-wave scattering, then the pole moves this way.
Okay.
Goes here, back there, which corresponds to this.
In the
K
K
plane.
Goes here in the K-plane and then up. Because you see it has a negative imaginary part which becomes smaller and smaller and smaller, then it's zero, and then it gets a positive imaginary part, so you get negative energy, positive negative energy again, but it is zero somewhere.
And this is let's say, this is a bound state.
This is Yeah, it starts out as a resonance, then it becomes a bounce, virtual bounce state, and then it becomes a bounce state.
A bounce state. In the end, it's a bounce.
And this is, you can prove this behavior with the effective range expansion.
Yeah, well, I've proven it with the effective range expansion, yeah, that's true. It's a bit complicated, but you can prove it.
And one typical example of this behavior for S-wave is the DS2317.
So here you
which
have
we
the DS
2317,
2370,
which is a CS bar meson, scalar CS bar meson, and it couples to decay threshold in an S-wave.
yes,
And in our paper we published in PhysRev Letters in 2003,
I remember.
we have put there the plots, and there you can exactly see this behavior.
And but essentially, let's say this is essentially the plot that corresponds to effective, how do you say, effective range.
No.
No. It's
No.
really
No. The effective range expansion you can use to prove that for S waves the behavior is like this, and that for other waves it must go through the origin directly.
So only in S wave it goes like that.
Yeah. Which means if L is different from 0, you do not create a virtual bounce state. You always go directly from resonance to bounce state.
So for L equal than 0, from L different from 0, you cannot have a
virtual. No, you go directly from resonance to bounce state.
Resonance in that to the other one, which is a bounce state. While on the contrary, in the case of S wave, you can have this. I can understand. Makes sense.
well, that's what we
And the virtual in that picture correspond. In that picture, if you put a tick on the virtual, is
just this piece, this lower piece. From here to here is virtual bounce state.
A virtual bounce state.
And then you continue with the coupling increase, and it becomes a bounce state. Here.
Okay.
Yeah, but be careful, you still can have virtual bounce states. You actually will have, because there are always two poles. So I think maybe I'm not correct here. Maybe it's still also with an angle. I don't remember. Or does it go quadratic? No, it must go.
I think it's smooth.
Yeah, it must be smooth. Well, not actually.
Of course, it does not exclude that there could be virtual bounce states.
There must be.
Yeah, but I mean that you would not call a virtual bounce state. But what do you call a virtual bounce state? It is a pole in the S-wave that is close to threshold, but the wrong frequency. Now, if it's here, it's not close to threshold.
No,
it's just a mathematical singularity.
This is a mathematical singularity.
If you have P wave or higher, they both go there close to threshold, and they become one bounce state, and you will have virtual. So you will always have.
So the virtual state
but
is
where?
Close to the threshold. But on the wrong, not on the physical, but because of analyticity, you feel it in, let's say, in the cross-section. So, like in the nuclear case, nuclear scattering, that you feel the presence of the virtual states in the 1s0 channel ratio. That corresponds to in the effective range formalism, it corresponds to a negative and big scattering length. It's my
okay. Yeah, but be careful, because scattering effective range formula, there is a convention there. And this convention, I think, is a nuclear physics convention. Sometimes in hadronic physics they use a different sign.
And why? Because this always made me confused.
Yeah, it is terrible.
Sorry,
sometimes.
I have to check with my husband that my son is safe. That he pick up.
Okay.
Sorry.
But here, of course.
This is my view.
There are priorities.
Otherwise I cannot stay relaxed. Mauro, hai preso Archie? Tutto a posto? Bene.